The next category of reactions we're going to look at are the replacement and displacement reactions. So you can see here the generic setup is going to be a single element and then a chemical compound. And what is going to happen here, we come up with the important phrase of the chapter where metals trade places, and we'll also talk about here how actually halogens can trade places. But this is going to be the generic format. You have an element by itself, you have a compound. That element that was alone trades places with some type of similar element that was bonded in a compound. Some of these reactions are spontaneous, some are not. So within the single replacement or displacement reactions, and again we can just abbreviate SR or SD, there are 4 subgroups. The first subgroup, again, is the one we've been talking about since day one. A metal that's alone replaces a metal that's in a compound. Here I have the simple designation of M and then M prime. So we have a metal by itself. We have a different metal that is bonded to X. And X can be anything as simple as chlorine all the way to something more complicated like sulfate or nitrate. What ends up happening then, we can see here that the first metal that's by itself ends up being bonded in the compound with X, while the second metal, M prime, that was bonded with X is now alone. So we can look at some simple examples here. We could take something like sodium and have it react with calcium chloride. And what's going to happen is calcium will end up being by itself in its pure form, and sodium will be bonded to chlorine. Now if you notice here, we have Cl2 on the left. We're not going to have Cl2 on the right. The reason being is sodium's a +1, chlorine's a -1, so +1, -1 cancels out, we're done. Now what we will do is come back and then balance with coefficients. So we put a 2 out in front of those places where sodium is. Okay. Another example, let's say we take magnesium by itself, bonded to potassium nitrate. And I just put the parentheses around nitrate just because. So what will happen here is the metals trade places, potassium be by itself, and now magnesium will be bonded to the nitrate. Now magnesium's a +2, nitrate's a -1, so we get MgNO3 2. We come back and we have to balance. We've got 2 nitrates on the right, 2 NO3s on the right. We need 2 on the left. Now we got 2 Ks. Now we got 2 Ks. So what I want you to do, just like we did all the other examples, write 2 other reactions, completely different metals. Don't pick sodium, magnesium, calcium, or potassium. Don't forget to also include some of the D block metals. The next one, these next 2 actually are there's some similarities to it, but there's one subtle difference that we have to pay attention to. Alright, so the next thing is a metal that's by itself can replace hydrogen in an acid. And I'm going to use the phrase total replacement. Here's our next phrase. We already said metals trade places. The second phrase is treat hydrogen like a metal, because hydrogen is an H+. So what we really want to think of, treat hydrogen exactly the same way you would treat sodium, potassium, lithium, or any of those other +1 metals. So here we have a metal by itself, and then we have it reacting with an acid in which it has hydrogen. So let's say we pick, let's say we pick copper metal, and just for reference we'll say we're going to use copper 2 metal. Again, if it doesn't say, you can pick which one you want. And let's say we react it with hydrochloric acid. So what's going to happen is this hydrogen is going to act like a metal, and it's going to trade places with copper. This is no different than if this would be NaCl. So what we're going to have is the metal, copper, is going to bond with the leftover piece of the acid, which in this case is simply chlorines. Now, copper, we said back here, is a +2. So if it's a +2 here, chlorine's a -1, we get CuCl2. And then the hydrogens are by themselves. Now don't forget here, hydrogen is one of those diatomic molecules, so it's going to be H2. We can have something a little more complicated. Let's say we take silver metal, be really expensive to use, and we bond it with sulfuric acid. Again, same thing holds true. The metal trade places with the hydrogen. We get Ags with SO4. Silver's a +1, sulfate's a -2. So we get Ag2SO4, and we get hydrogen gas. Now we do need to come back up to both of these examples, and we can't forget to balance. Okay. So pick 2 other metals, 2 other acids. Work through those examples and show me what you've got in class. Next example. Now here's where we have some similarities. We've got a metal replacing hydrogen. So we want to treat hydrogen like a metal. So that's the same as the last example. The difference is it's not acid. It's not hydrogens in acid, it's hydrogens in water. So we're going to use this phrase, partial replacement. So what that means is it trades with some of the hydrogens, not all of them. So we still treat hydrogen like a metal, but here's the second piece. We want to think of water as the chemical HOH, not H2O. So we think of water as HOH, just like we would sodium hydroxide, potassium hydroxide, lithium hydroxide. We treat it exactly the same way. Metals trade places, hydrogen acts like a metal. So here we take, let's say I take iron. Let's say it's iron 3, just for our example here. And we react it with water. So what's going to happen is that metal is going to trade place with some of the hydrogens. And the reason we write it as HOH, we're basically saying it's going to trade places with that first hydrogen. Okay. So we're going to get iron bonding with hydroxides. Now iron's a +3, hydroxides are a -1, FeOH3, plus we're going to make hydrogen gas. Got to balance charges. And again, this one just gets kind of messy here. I got 3, 4, 5 H's. I got 3 O's. Okay, well, I put a 3 out in front here. That takes care of the 3 oxygens. I now have 6 H's on the left. I've got 3, 4, 5, 6 on the right, 5 on the right. And this is kind of messy. So I put a 3 here. That makes 9. Come over here. Well, that doesn't really help. So here's what you're going to end up finding is erase. Pick a different number. So you know what? I got 3 oxygens. There's 3. I got 6 H's. Well, what if I did something like this? Well, what if I doubled this? And say, well, now I got 6 O's and 6 H's. Well, now if I put a 6 out in front here, I actually now have 12 H's on the left. If here I have 6 H's, I put another 3 out, and I've got another 6 H's. A little bit messier in the balancing, but you can figure it out. Let's do another example here. Let's say it's lead, and we'll say it's lead 2, reacting with water. Lead will trade places with the some of the hydrogens. So we get Pb with OH. Lead's a 2, OH is a -1, so we get OH2. And then we get hydrogen gas. 2 oxygens and 4 hydrogens. Put a 2 out in front. We're all set. Okay. Pick 2 more. The last one. Treat it the same way, except instead of the phrase metals trade places, we're going to use a halogen replacement, which means halogens will trade places. So simply an halogen by itself will trade places with a halogen that's in a compound. The only difference you see here is we're going to use the letter X and X prime to represent the halogens. So imagine here X2 is, let's say we have fluorine by itself, and then we have chlorine bonded with a metal, in this case sodium. Well, fluorine's not going to trade places with sodium, fluorine's going to trade places with chlorine. So what we'll end up getting is chlorines will be by themselves in pairs, and sodium will bond with fluorine. And we have to balance. We could have iodine by itself, bonded with copper to bromide. So now we're going to have bromines by themselves and coppers bonded to iodines. Right. Obviously there's not as many combinations here since we only have 4 metals: fluorine, chlorine, bromine, and iodine. But still, pick 2 more examples and look at those. Alright, double replacement. Okay. This just plays off of the single replacements. The only difference here with double, we don't start with a single element or a single atom. Now we start with 2 chemical compounds. And again, it's still replacement, displacement, so the whole trading still occurs. Again, some of these are spontaneous, some are not. We'll worry about that later. 2 subgroups. The first one, a metal that's in a compound will replace another metal that's in a compound. So metals are still trading places. The difference is, in double replacement, neither metal is alone. They're both in a compound. In single replacement, one of the 2 metals is alone. Now, we can apply also hydrogen to this, so it doesn't have to be just a metal. It can be hydrogen that is in a compound. So we've got M and X, M prime and X prime. So let's pick, let's see, cobalt, and we'll say cobalt sulfide. Okay, in this case it's cobalt 2. Reacts with magnesium chlorate. So, simple rule, metals trade places. We're going to get cobalt with chlorate, and we're going to get magnesium with sulfide. Now the combinations I picked here, cobalt's a +2, sulfur's a -2, magnesium's a +2, chlorate is a -1. So put a 2 out in front there, and we're done. It's kind of an easy example because it didn't change anything. So let's mix it up here. Let's say we choose aluminum sulfide, and we pick strontium phosphate. Metals trade places. Aluminum will now go with phosphate. Aluminum's a +3, phosphate's a -3. Strontium then will go with sulfide. Strontium's a +2, sulfur's a -2. So on the the right-hand side, the subscripts kind of are nice and neat. We come back over here, we balance, put a 2 out in front of the aluminum phosphate, put a 3 out in front of the strontium sulfide. Alright, 2 more examples. Make sure again you show me in class. Alright, then halogens in a compound replace another halogen. So now here it could be, let's say, manganese chloride, and we'll say it's manganese 3. Reacts with calcium bromide. Sorry, a little messy there. Try that again. Calcium bromide. Now what we're going to get here is manganese bonding to bromines and calcium's bonding to chlorines. Manganese is a +3 on the left hand side. So it stays a +3, calcium's a +2, chlorine's a -1, and we get that. So what we'll have to do, balance here, 2, 3, 2, 3. Okay? Again, you just see halogens trade places. I should be able to figure that out, so I'll just do one and you can pick 2 more examples. Alright, so we've gone through the next 6 examples, the next 2 big categories which they had subgroups. The single and double replacement or displacement, where the phrase metals trade places, hydrogen acts like a metal, and halogens trade places. So those are our 3 phrases that you got to think about now. Metals trade places, hydrogen acts like a metal, and then the third phrase, halogens trade places. Alright, so very last reaction. Oh, sorry, one more thing here before we get to this. You're going to see these terms, so sometimes they get confused, so just want to remind you here. If you see the name ammonium, here's what you got to remember is this is the ammonium ion. It is not a standalone chemical. It is NH4. It has a +1 charge. We treat this like a metal, like a sodium. Okay? NH4 ends up being bonded to something else. So for example, we would have ammonium chloride, NH4Cl, just like we would have sodium chloride, or ammonium, fill in the blank, ammonium sulfate, ammonium nitrate. Now if you see ammonia, ammonia is simply NH3, and this is a chemical compound. So ammonium, again, is an ion. Ammonia is a compound. We will not have ammonia chloride. We will have ammonium chloride. Okay? So again, that'll start popping up more and more, so hopefully we can recognize that. Alright, so the very last category, combustion reactions. Okay? These are obviously the reactions that go boom. Just in general, a combustion reaction really is any reaction in which a chemical burns, and most chemicals burn in the presence of oxygen. More specifically, we're going to look at what we call carbon-hydrogen compounds. These are often referred to as hydrocarbons. So we're going to look at what happens when hydrocarbons burn in the presence of oxygen. Well, when they burn in the presence of oxygen, they make 2 things. They make carbon dioxide and they make water. Now here's the thing, the formula for these hydrocarbons can be, I shouldn't say every combination of X and Y, but certain combinations of X and Y. And we'll see some examples here in a little bit. The only thing that is going to be different, whether this X is a 2 and the Y is a 4, whatever these numbers are for X and Y, it does not change what the reaction does. The only thing it will change will be the coefficients that everything has. So for example, 3 hydrocarbons that you've probably heard a little bit. Methane, propane, and butane. So methane gas, propane, yeah, some of you have propane tanks for heat. And then butane lighters, you know, the little automatic lighters. Those have butane. Even another one that's not on this list that we can quickly talk about, octane, the main ingredient in gasoline. Okay. So here's the deal about these hydrocarbons. Any of them can react with oxygen. And when they react with oxygen, they're all going to form carbon dioxide and they're all going to form water. The only difference is going to be how much oxygen, or I'm sorry, how much carbon dioxide and how much water. Obviously, if we have a chemical with more C's in it and more H's, we're going to make more carbon dioxide and we're going to make more water. And that's it. So it's really easy to remember what the products are. What takes you a little bit of time is going to be the counting or the balancing of the atoms. So real quick here, I'll do the first one for you here. You'd say, okay, well, if I'm trying to balance this first one, if methane gas reacted with oxygen, we're going to get CO2 and water. So what will happen here is I've got one carbon on the left, I got one carbon on the right. I've got 4 H's on the left, I need 4 H's on the right, so I'd put a 2. I've got 1, 2, 3, 4 oxygens on the right, 1, 2, 3, 4 oxygens on the left. What I want you to do is work on the, the second one and third one. I want you to do on your own. We probably will have to talk about a little bit of balancing that you'll have to pay attention to with this third one. The reason being is the number of hydrogens involved and oxygens. We kind of get an odd and even number thing. But what I'm going to do is let you kind of figure that out on your own. And at some point, I'm sure in class, we will talk about the little thing you got to watch out for to balance some of those combustion reactions. It's not that difficult, but you got to do a little bit of counting that you need to pay attention to. So that's it for that then.